Okay, here's the data analysis worksheet for the azide binding and the protein quantitation by Bradford method lab. We're going to go through the worksheet point by point, and I will tell you where to find the process in order to calculate these values, or I'll show you what the process is. So let me grab a pen and we'll go through it point by point, and hopefully this will answer some of your questions. So for the first point here, take the graph you make the KD determination below. Differentiate between equine and bovine myoglobin. So the graph for KD determination you will have generated using the template Excel file. You will need the solver in order to do that. And there is a video on Canvas. There's also an instruction sheet on Canvas that shows you how to do that. And where I say differentiate between equine and bovine myoglobin, you're going to have a graph. And on the graph, you're going to have the A540 nanometer value, and absorbance, remember, is unitless. On the x-axis, you're going to have azide concentration, and that's measured in millimolar. You're going to have two curves on here. One curve is going to be for your equine myoglobin, and one will be for your bovine myoglobin. And so I'm asking you to please make sure that you have an appropriate legend which indicates which curve belongs with myoglobin from which species. Next, you're going to be reporting formally those KD and those A540 nanometer theoretical maximum values here. And please make sure that you continue to differentiate between equine and bovine myoglobin and use proper units. So the KD is in units of essentially molarity, and make sure that you use the proper exponent or the proper prefix for the metric system to report that in the proper order of magnitude. And remember that absorbance is a unitless quantity. I think this next point is where a lot of students had difficulty, and that was in figuring out the concentration of protein in your unknown samples. So I want to go through this with you to make sure that you see how to do this. And this is a commonly used method, right, for determining concentration of an unknown sample. I'm not going to go all the way back to Excel and show you how to make the graph. So please do make sure that you rely on help videos and peer support for how to use Excel and generate a graph. But I will show you what should be on each axis. Your dependent variable is what you measure experimentally, and that, by standard convention, is usually placed on the y-axis. So this is the dependent variable. This is what you measure. The dependent variable, what you measure, depends on your assigned category or your assigned characteristic. The assigned category or the assigned characteristic is your independent variable because it's what you assign. And by standard convention, the independent variable is placed on your x-axis. In this case, the independent variable is the BSA concentration of your stock, and you can actually just use milligrams per milliliter or mgs per mil. When you plot your data, you will get a series of points that look something like this, and you will do a linear fit of your data in Excel, and please report the equation on the graph and also the r² value on the graph. And so you will have some equation that is done by a least squares regression in Excel for you. And you get this equation on the graph. This equation will now permit you to determine the concentration of protein in your unknown samples based upon the known concentration of BSA in each standard curve point. Let's back up a little bit because I want to make sure that it's clear to you what we did experimentally. Here's a quick review of your experimental setup for the Bradford reagent. So you had a couple different standard points to work with, and they were bovine serum albumin of known concentration. So these are your standards, and they are of known concentration. You also had a set of cuvettes, and for each curve point and your zero, you had a separate cuvette. And what did you put in the cuvettes? You put 1,000 microliters of Bradford reagent, and then you added 20 microliters of each of your curve points. And of course, 20 microliters of your buffer. Now, I told you, as spectroscopy purists will do, zero the spectrophotometer to air, and then we're going to do a mathematical correction for the contribution to the absorbance at 595 nanometers due to the Bradford reagent itself. So we did essentially a math zero here. So you set up your standard curve points, but that wasn't all you did, right? You set up also some unknown samples. Let's take a look at the unknown samples. So down here, on this side of the line down here, we've got our unknown samples. I mean, we know what they are, right? But what we don't know is the concentration. So the unknown concentration samples. And the first sample that was prepared was, depending on what column you ran. So we had the ion exchange column and the gel filtration column. The material that came off of the gel filtration column was much more concentrated, and so we need less sample. And I think that I asked you to dilute that 20 microliters of your column fraction and 180 microliters of buffer. And so both of these materials were added into this snap cap, okay? So there's two things that were added in. The ion exchange samples were much more dilute. And so we had, I believe I asked you, 60 microliters of the column fraction and 140 microliters of buffer. So put both of these items in here. So we had combined those two things, right, depending on your column that you ran. Please refer to the exact dilution on your lab protocol to make sure that my memory is correct. But this dilution factor is important, and we're going to come back to it in a little bit. Crude lysate or beef extract was diluted 10 microliters of crude lysate. So I'm going to put 10 microliters of crude and 190 microliters of buffer. So this snap cap, right, you put two items in there. And this is the material, this crude lysate beef extract was the starting material applied to the column, okay? Now, cuvette number 3 was prepared at the end of your azide binding study, and cuvette number 3, right, which was here, cuvette number 3 contained 50 microliters of your myoglobin standard, and that was the equine myoglobin standard, plus 950 microliters of buffer. So essentially, your cuvette 3 sample or the myoglobin standard, these two are equivalent. So you didn't even need the snap cap for this part because you could take material directly from that cuvette. Now, we processed these unknown samples identically to how we process the standard curve points. So to each of these 3 cuvettes here, we added 1,000 microliters of Bradford reagent. And then we added in 20 microliters of sample. So 20 microliters of sample and 20 microliters of sample. Because everything is the same as far as the volume that we added to the cuvettes, we can make comparisons directly. So we added 20 microliters of each of these standard curve points and 20 microliters of each of these unknown samples. So it makes the math very simple. When we do the graphing, we can report the BSA concentration in our standard points directly. So this would be 0, 0.25, 0.5, 1.0, 1.5, and 2.0. And because we used the same volume of the standard curve points and the same volume for our standards, we can do this. So if we take 20 microliters of a 1.5 mg per mil standard point, we get a particular absorbance, and that absorbance that we read, tells us that, this came from 20 microliters of a 1.5 mg per mil sample, or excuse me, mg per mil standard point. So I just want to show you that the units, everything here is legitimate and it all lines up. So we plotted our data and we got a fit equation from Excel. What do we do? How do we use this fit equation in order to determine the concentration of our unknown samples?